All right, let's get started. Okay, I want to quickly review the subset construction again, just to remind ourselves of NFAs and DFAs and things like that. So recall what we did towards the end of last lecture. We proved, or sketched, we did not prove, we sketched a proof or a construction to show that if I have an NFA that recognizes some language, I can construct a DFA that can recognize the same language, right? So in that sense, the NFAs are not any more powerful than DFAs, even though they look more powerful, right? But we'll see that they're somewhat more powerful for other reasons. But what was the idea behind the proof? The idea behind the proof was that, look, if I have an NFA and I want to build a DFA that recognizes the same language, because it's abstract, right? I don't know a concrete NFA. I can't go to the language and then come back and say, oh, for that language I can define a DFA. The way we want to do it is like we want to simulate the NFA's behavior by a DFA, right? So how do we simulate the NFA's behavior by a DFA? We say, oh, look, whatever NFA is remembering or can remember at this thing, the DFA should do the same thing, right? So what can the NFA do? The NFA can be in multiple states, right? That's the idea. So we say, oh, let's make the DFA remember all the potential states that the NFA could be after reading some part of the string, right? So the state space of our DFA would be the set of all subsets of the NFA states, because it could be in any one of these potential states, right? So that is how we define the state space. So now we also have to figure out what are the accepting states and what are the transitions. Well, you know, when does an NFA accept a string? If it can reach some accepting state, right? So if you think of it that way, they'll say, oh, in our DFA, remember that our states of the DFA are subsets of the states of the NFA, and the meaning that we want to ascribe to that state is, if I'm in that state, it means that, you know, starting at the start state of my DFA, after seeing a string, this is the set of all states that the NFA could reach on that string, right? So when should our DFA accept? If any one of those states is an accepting state, the DFA should accept, right? Because that's what NFA would do, right? That's a definition of NFA accept. So okay, so here is a simple NFA designed specifically to make it very simple. It has only 4 states and very few transitions, as you can see, right? And ideally, our NFA should have 2 to the 4, I mean not ideally, our construction says we have to have 16 states in our DFA. But I'm only showing 4 here because these are the only 4 states that the DFA will actually be able to reach from a start state. So we don't want to start with all possible 16 states and realize later on that many of them are not reachable from the start state. Ideally, we like to build it only those states that are really useful in the DFA. So how do we do that? We say, okay, what is the start state of my DFA? Well, you know, we look at the NFA start state and say, what could the NFA do on the empty string? That's what our DFA should do, right? What will the DFA do from a start state on an empty string? It will just stay there, right? The DFA cannot do anything on the empty string then other than stay where it is. But the NFA can do funky things, right? What can the NFA, where can the NFA go from a start state on epsilon? All the epsilon reach of the start state, right? So that will be our start state. So if you look at this NFA, where is the epsilon, what is the epsilon reach of its start state? It is Q0 and Q1, right? So that is the start state of the DFA, yeah? Okay, now we know one state of our DFA, right? The important state, which is the start state. And then from there we have to build, right? You know, we have to say, okay, this is the start state. What are all the places that it could go on 0? What is the meaning of that? It means that in the NFA, if I start here on a string 0, where can it reach? Well, it can already reach on epsilon Q0 and Q1. Now we want to say on 0, where all can it reach? Okay. Now, okay, we have to figure that out, right? We have to figure out from Q0 and Q1, where all can we reach on 0, and it turns out it is Q3, only Q3 can be reached. And how do we figure it out? Okay, first we build a small table, and then we build a big table, right? What is a small table? We look at only the states of NFA, Q0, Q1, Q2, Q3, and then we say, okay, where can it go on epsilon from each of these states? It is the epsilon reach, right? So we can build that, right? Okay, where can Q0 go on epsilon? It can go to Q0, it could stay in Q0 or go to Q1, right? So this is the epsilon reach of all these states. Good? Okay? Now what about on 0, the string 0, not just the letter 0, where can I go from Q0 on string 0? Okay, I can do it like, I'll look in all possible things, but how can we do it mechanically? What is the definition of where all can I go from Q0 on string 0? First I say, where all can I go on epsilon, right? Okay, I can go to Q0 and Q1 on epsilon. From there I take a 0 step, right? Okay, from Q0, Q1, if I take 0, where will I get? Well, from Q0 on a 0, I can't go anywhere, right? But on Q1 on 0, I can go to Q3, okay? Okay, so Q3, I can at least reach Q3, but from there, maybe I can take an epsilon reach also, right? I can go on an epsilon reach, but what is the epsilon reach of Q3? It's Q3 itself, right? There's nothing. So I end up with Q3. So on string 0 from Q0, I can only go to Q3, right? Okay, but what about 1 though? Where can I go from Q0 on 1? Okay, again, we say, okay, it can go on epsilon to Q0, Q1, that's the epsilon reach, right? Without seeing anything, I can go to Q0, Q1. And then I can take a 1 step, right? But I could go to multiple states from 1 step. What can I go from on 1? Okay, if I'm Q0 on 1, I can go to Q2, right? And if I'm in Q1 on 1, where can I go? I'll die, right? Okay, so, I go to, so I claim that I can go to Q2 and Q3 on 1 because I could stay at Q0 after seeing epsilon, and on 1 I can go to Q2, right? Okay, but then I could also go from Q2 to on epsilon to Q3. So Q2 and Q3 are the possible places I could be if I start in Q0 and see a string 1, right? So we can fill this table first, right? So that is only for single states. What can I do on epsilon? What can I do on 0? And what can I do on 1? Okay, so you create a small table, and then how do we figure out what we should do with this thing? Now, what is the definition of this? The definition of this is that, on 0, where all can I go if I am on Q0 or Q1? Right? Well, we already know where we could be on Q0, Q2, Q3, Q3, and what can we go? Where can we go from Q1? Only Q3. So the union of this is again only Q3, right? So that is the state I have to go on 0, right? Okay, what about Q0? If I am in Q0 or Q1, if I see 1, where can I go? Well, let's go and look in this table. If I'm in Q0 on 1, I can go to these 2 states, right? If I'm in Q1 on 1, I can go to only the empty set. So the union of this is what? Q2, Q3. So that's the state I go to. Okay? So that's it. Once you build this table, building this NFA is easy, right? So this is the building block. Even to build this thing, you have to first say epsilon reach, then 0, then 1. Okay? It's mechanical but painful. Okay? Yeah? The algorithm is clear, right? Okay, so how do we prove that this is correct? You can see the formal thing. To prove that it is correct, what we need to show is that our DFA is actually simulating the NFA, right? What does it mean? Just like we did with the product construction, remember we started with an NFA and we formally defined a DFA, right? Based on the subset construction. We have to prove that for every string W, what is this? Delta star NSW. What does that mean? What is this? This is the transition function on the strings of our NFA, right? So this is a set of states, remember? Because it's an NFA, I can be in many possible states, right? This is a set of states, right? Okay, but what is this? This is a transition function of the DFA that we created, okay? Yeah? And this one is its start state. And what is this? Is it a set or a single state? single state because it's a DFA. A DFA can only be on a single state, right? Its behavior is deterministic, right? Okay? After seeing a string, the DFA cannot be in multiple states, right? It will be in only one state. But how am I equating a set to a single state? What does it mean? Yeah? Yeah, because the state space of the DFA is the subsets of states of the NFA, right? So this is actually a single state of the DFA, but what is a single state of a DFA? It's a subset of the states of NFA, okay? So that's why this is a set, but this is a singleton in the set space of the DFA, okay? So what is the meaning of this? The meaning of this is that if the NFA is started on its start state and you give it a string W, it can go to many possible states, right? Okay. This is saying that, okay, this DFA is simulating that. What does it mean? That its states are the subsets of the states of NFA. On the same string, it will go to a deterministic state, which is the set of all states the NFA could have been on that same string W. This is a simulation argument, right? That is the construction is built that way, right? We are trying to simulate what the NFA could potentially do, right? What is its operational meaning? This is the operational meaning mathematically. Yeah? Okay, now once you, most of the job here is to make sense of this mathematical statement. Once you make sense of the mathematical statement, the rest of it by induction is mechanical, okay? You have to say, oh, this is what this statement means. And now let's see how can we prove it by induction. Well, we proved by induction because we built the machine like that, right? Our machine was built to maintain this property, right? It didn't come out, the proof doesn't come out of some magic. We actually, that is the idea behind simulation, right? This is what we want to do, right? And we built it intuitively that way, and we will now have to check that this is really indeed happening, okay? So the rest of the proof is mechanical. And I'm not going to do it in class because it's not going to happen so quickly. So, you read this, it is not very long, except that, it just is symbol manipulation. It looks like, it's just definitions, okay? You have to make sure that you have defined things properly and step through the inductive proof. It's not long, but the whole point is to figure out whether the formalism is actually making sense, okay? All right, so I won't do the formal proof because it's fairly mechanical once you understand the meaning of it, okay? Okay, so that's a review of a subset construction, okay? But you need to understand about the subset construction is that the interpretation of the states of the DFA that we created, okay? So this is useful for you in doing problem 3, okay, on the homework. Okay, now let's briefly discuss the closure properties of regular languages. So maybe, we didn't formally define it. When we say closure properties, what does it mean, right? As I said on the piazza, we think of the set of integers, right? We say that the set of integers is closed under the operation addition. What does that mean? So we have an operation called addition, which is defined on not only integers but rationals on real numbers and stuff, right? What does it mean that integers are closed under addition? If you add two integers, do we get an integer or do we get something outside integers? You always get an integer, right? So the set of integers are closed under addition, right? Also same with multiplication, but they're not closed under division, right? If you divide two integers, you will not get an integer, right? Okay, so when you think about closure properties of regular languages, what are you saying? We are saying, look at all the set of regular languages, right? They are a subset of the set of all languages. Okay, we don't know whether it's a proper subset, but it is a subset, right? Because they're languages, so they are clearly a subset of the language. These are a special class of languages. What properties do they have? So if you take two regular languages and take the union, do I get a regular language or do I get out of the regular languages? We get a regular language, right? But so why is that? Because when we defined regular languages, we said if two languages are regular, then the union is also regular. That is our definition of regular languages, right? But when we defined, it is not obvious right away that if I take a regular language and I complement the language, I get a new language. Is it also regular? It wasn't obvious, right? From the original definition of regular languages, we define it as oh, it is closed under union, that is by definition, and it's closed under concatenation, and it is closed under clean star. Okay? But then later on, we realize that, the regular languages, the way we define it, are the same as the set of languages accepted by DFAs, right? But DFAs, we know that if there is a language that is accepted by DFA, then its complement is also accepted by DFA, right? So regular languages are also closed under complement, right? Which is nice, right? You know that if you have a machine for a language and I have a machine for it's a complement, right? And so why only these operations, right? You can define many operations, not just union, intersection, clean star, and many other operations. And as you can see, that this, a set is closed. That it comes from the notion of closure, right? And that means that we're not getting out of the set. We are closed community. What does that mean? We don't want to get out, right? Okay, not necessarily a good thing in social life, but here it is useful. Okay. So one thing to so mathematically, one thing to note here is that the different representations allow us to prove different things nicely, right? Different characterizations of the same object, the set of regular languages. Oh, they're also the same as the set accepted by DFAs. Oh, they're the same accepted by NFAs. Helps us prove different things, right? And so you can ask, oh, we already did complement, union, intersection, and the proof was easy via DFAs. While union, concatenation, clean star was easy via the inductive definition or via NFAs. Okay? Okay, there are many operations that you can define on languages. Homomorphism, inverse homomorphism, reverse. And regular languages are very beautiful because they are closed under many of these operations. Okay? What that means practically for me is that I can give you a lot of funky problems. Okay? I know, but it's really why do we study DFAs? Because they are a very nice and beautiful, simple class of languages which are still useful and they have many applications as well, right? Okay, so to do this, I want us to understand this as an exercise. Okay, so suppose I give you a language, I will define an operation called prefix, right? It's for any language, it's not just for regular languages. For any language, I can define a new language called prefix. What is it? You take every string in the language and you can take all its prefixes and throw it in this language. Okay? No, a prefix is something that comes at the start of anything which starts at the start of the string and goes part way. It can go all the way. Okay? Yeah. So is this operation okay? If I have a language, prefix L is another language, right? Yeah. Okay? Okay, so it's defined for every language, right? Now the question is, I claim that if L is regular, then prefix L is also regular. Okay, what is the meaning of this? So if any language that is regular, all its prefixes are also, you look at the language defined by the prefixes, that's also going to be regular. So that means that the set of regular language is closed under the prefix operation, right? Whatever the prefix operation is, right? See, what does the prefix do? It takes a language and spits out what? Another language, right? So when we say something, the set of regular languages is closed under prefix, what it means is that if you take a regular language and take this prefix operation on it, you'll get another regular language. It's not obvious that it's true, no? Okay? So, okay, why is this? So how do we prove this, right? This is where, it's a little tricky because we are proving a meta theorem, right? I don't have a single language L that is regular that I am trying to prove the prefix of is regular. I have to prove it for all regular languages in some sense simultaneously, right? That means I need a meta proof, right? What does it mean, a meta proof? I should just say, oh, how do I prove it for all regular languages because there are infinitely many regular languages, right? So my proof technique has to be meta proof, right? So how do we do it? Okay, you say, what does it mean that a language is regular? You have a choice to use the representation that is most convenient for you. You can say, oh, it means that either it has a DFA accepting it, right? Or it has an NFA accepting it, or I can write a regular expression for it, right? Yeah? So I want to say, okay, what is the nicest representation? The most constrained representation to some extent is a DFA, okay, because it's deterministic in some sense. Maybe that's not obvious, but you say, aha, if it is regular, that means that there's a DFA that accepts it, right? Okay, so there's a DFA that accepts it. Now, can I create a DFA that accepts the prefix of the language accepted by this machine? Okay. If I can do that, then I'm done, right? Because I did not assume anything about it other than the fact that there is a DFA for it. I'm going to create another DFA which will accept precisely the prefix of the language accepted by this DFA. If I can do it, I'm done, right? Because it's a proof for all regular languages simultaneously. Okay. Now let's think. How can I create, I know that, this DFA accepts this language L, right? What DFA will accept all the prefixes of the language? Okay. A equals to Q, okay. Not quite, okay. If A equal to Q, then I accept sigma start. Okay. So he's saying, I take the DFA, I have a DFA which accepts some language, right? What is it? What are the strings it will accept? What does the DFA do? What are the strings that DFA will accept? Anything that goes from start state to some accepting state, right? Now I want to accept the set of all strings which are prefixes of those strings. So I want to say modify my DFA to do that. Create a new DFA, right? And he's saying one easy suggestion he said is, I'll take all the states and make them accepting states and get a new machine that will accept prefix of L. I claim that's not true because if you make all the states accepting of the original DFA, I'll accept everything, no? But that will give me sigma star, but maybe I have strings. My prefix might not be the set of all strings, right? Okay, yeah, okay, lots of hands, okay. Okay, okay, so let's see, okay, let's try to understand what should I accept, right? Okay, I should accept the string W. My new machine should accept the string W if what happens? That, let's call M should accept W if there exists some string X such that Wx belongs to L of M, right? That means if there is some way to go, add another string X so that I can get to the accepting state of the original machine. Okay. So then what does it mean? That means that let's see what the machine M will do on W. Where will it be? It will be in some state, right? Okay. And from there, how do we know if I'm in a state of my original machine, whether I can go to a accepting state of the original machine? I can so any state that I can reach from the start state should become an accepting state if there is a path from that state to some accepting state of the original machine. Okay, so think of a machine like this, right? Let me give you a concrete example. Okay, so okay, suppose this is my start state of the original M. There is some state which is a state like this, and there is some other state, and okay, this is my original DFA, right? Okay, so look at this state, right? If a string takes me from S to this state, what will happen here? I'll get stuck, right? Because there are no transitions out of that. Okay. So any string which takes me from here to here is not going to be a prefix of something that my original machine will accept, right? But look at this state. If a string takes me from S to this thing, then I claim that means I can go from here to an accepting state, right? So that means that any string which takes me from S to this state is a prefix of something that is accepted by my original machine. Okay, right? So my claim is that my new machine is the same as the old machine except that I increase the accepting states. And what should be the accepting states? Any state of the old machine such that there is a path from the start state to that state and a path from this state to some accepting state of the original machine. It is possible that it's all the states, but it is possible that it's not all the states. Okay, right? So it doesn't make sense? Yeah. So that is how we prove that prefix is also, that is, I created a new DFA for you which accepts precisely the prefix of the language accepted by the old machine, right? Is that okay? Okay? No? Yes? No? Yeah. So that's how we do. It's a meta proof, right? Why is it a meta proof? We don't know anything about M, right? We just said, there is an M, so we're going to alter that M. And then we say, whatever that machine's language was, now we are creating a new machine for the prefix of that language. So the proof works simultaneously for all machines, right? Because it's a meta proof. Let M be an arbitrary DFA, right? That's how we prove properties, okay? All right. Now, what about a quick thing? What about suffix? I mean, it's formally defined. What about suffix? What is the suffix of a language? All the suffixes. That means that I can attach a string to the front so that the resulting string will be accepted, right? Okay, okay, how do you prove that this is also, regular languages are closed under this, right? So if I give you a DFA for this machine, I give you a DFA, right? It accepts a class of strings, right? How can I modify the DFA so that it accepts all the suffixes of the? Yeah, so it's tricky. It's a little, so we should accept a string if I can tag something onto it, right? Yeah, so which one is, yeah. So it's very similar to prefix. You had a, no, not necessarily next state. No, I can go around and go to the accepting state.
No, I'm saying if you're in the accepting state, if you can leave from that point, that would be an accepting.
Not sure I understand it, but let's see. Look at this picture. Okay. Yeah.
Now, if you, let's say you erase the top
one. This one?
Now, let's say we
to the top, okay.
Yeah. Then that state will become an accepting state for suffix.
That state should become an accepting state for suffix? Not necessarily. Well, it depends. Okay. So in suffix is a little tricky because we are not seeing the original portion of the string, right? So can you create an NFA for it? Yeah? Okay. So he's saying, there is no e-reach because it's a DFA. Okay. I'll tell you the solution just because it's a new concept for you, right? Create an NFA as follows. Create a new start state and put an epsilon transition to any state which can go to an accepting state. Okay? And that's it. Okay. So what does it mean? That the NFA can jump without seeing the first part of the string to a state that can reach a final state, right? Okay? Because it's skipping reading the first part of the string because we have to accept all suffixes, right? Okay? And, or think of altering the accepting states. So we're making the start states are different now. Not the accepting states, but we're changing the start states to misreading the prefix that we can't see. Okay? So it's a little tricky. You need to think a little bit, right? But the ideas are basically that you look at the DFA's behavior and understand what are the strings we are supposed to accept and see if you can modify it by either you can make an NFA out of it, or a DFA or give a regular expression so that we precisely accept the strings we want to accept. Okay, all right. Okay, so this is the idea of proving closure properties like this is you'll get I mean the labs is a bit behind, but you can look at the lab to see many simple examples of such properties. Okay, questions? Yeah. Oh, so what you do is, you basically create a new start state S prime, and you put an epsilon transition to this and to this. Okay, but not to this guy. You don't put an epsilon transition to this guy, because this guy cannot reach a. I mean, no. In fact, you can put an epsilon transition to any state that is reachable from the start state. It's okay. They will not lead to any accepting state. That's okay. No, you cannot put epsilon to accepting states, because what if the accepting state is not reachable from the start state? That's dangerous, right? You should not put an epsilon to the accepting state. See, suppose I have a piece of the DFA which is not connected to the start state at all. I shouldn't put an epsilon transition to that because it's not reachable from the start state. You can, yeah, you can put, yeah, you should put actually epsilon to every state that is reachable from the start state, and then that's enough. Okay, there are many ways to do that, okay, but you have to understand what we are trying to accept. All right? Okay, so that is about closure properties, that regular languages have this many nice properties that they are closed under, and that gives a lot of power when you prove things. And also, I mean, if you know that they're closed, you can save yourself design thing, right? You don't have to design fresh if you can use closure properties. Okay, so this is the last piece of the puzzle for regular languages, and this is proving non-regularity, right? What does that mean? So we saw that regular languages are characterized by this nice three ways. The obvious question is, is everything regular, right? Like, are all languages regular? It will be very nice, right? So we can do, because the machines that recognize regular languages are so simple, that will be very nice, right? But that seems like far-fetched. So now the question is every language a regular language? Okay? And the obvious answer is no, and let me recap the obvious answer of why it is no, right? Here is a simple way of seeing it is no. Remember, remember what are regular languages? They are captured by what? DFAs, right? So, how many DFAs are there? How many DFAs are there? Obviously infinitely, right? But are the number of DFAs countably infinite or uncountably infinite? Why are the number of DFAs countably infinite? Yeah? Yeah, sure. That's one way of doing it, right? But that's implicitly what you're doing, and which is, at a high level, it's even easier than that. I mean, in the following sense, every DFA you can write down in some how do we think of a DFA? It's a tuple, right? So it's just a string, right? To describe a DFA, I can just write a string, right? I just describe the graph to you. Okay? So you fix an encoding that you like, any encoding you like, right? But if I say, what is a DFA? It's just a string, no? You say, you have to tell me what the states are, you have to tell me what the alphabet is, you have to tell me what the delta is, you have to tell me what the start state is, you have to tell me what the action, right? How do you tell me? You just write down, no? Yeah? So you can represent, you fix an encoding, you have to figure out, what does it mean to write it down in a thing. You have to use parentheses, how are you going to represent the states, how many states? But doesn't matter, right? It's just a program, right? Every program can be written as a string in some larger alphabet. Maybe you have to use parentheses, you have to use something, right? Some other extra symbols. But at the end of the day, a DFA can be represented using what? A string, right? Over some finite alphabet. So how many DFAs are there? is no more than the number of C programs either, right? It's just no more than the number of strings over a big alphabet, right? So it is countably infinite because the number of strings is countably infinite, right? Okay, so hence the number of languages is countably, number of regular languages is countably infinite, right? But the number of languages we already saw is uncountably infinite, right? Because it's the power set of the number of strings. So there are way too many languages compared to number of even C programs, right? So clearly there should be some non-regular language. It's a very simple meta proof, right? But it's not interesting proof, right? Why is it not interesting? Because we don't have any understanding of what specific language is not regular, right? It's not telling us anything interesting. So what we want is, we want something, a better proof, better understanding of what is not regular, right? Because we don't care that there exists some non-regular languages. We want to know, this language, is it regular or not regular? Which is interesting to me, right? Not that there is some non-regular language. So here is the canonical non-regular language, and we'll see how to prove it. So look at this language. It's the set of all strings with equal number of zeros and ones, with all the zeros coming first, right? So what is the formal definition? 0 to the k, 1 to the k, k greater than, sorry, this should be k, sorry. So what is it? Epsilon 0 1 0 0 1 1 0 0 0 1 1 1 0 0 0 0 0 4 zeros 4 ones 5 zeros 5 ones, all those strings. Okay, why is it not regular? I claim it is not regular language. What is your intuition for it? Okay, so if it is regular, that means that we should be able to design a DFA for it, right? Okay, but DFAs are even restricted. Think of it as a program which has to keep only a fixed memory, right? Okay, why does this look like this cannot be done with fixed memory? K is arbitrary, yes, that's true. So what does it mean? Yeah. Yeah, so if you want to write a program without thinking about DFA, so what would you do? You would count the number of zeros, then count the number of ones, and then say, are they equal, right? Can you avoid counting is a question. Okay. Right? Our intuition suggests that, why can we not avoid counting, right? I don't know. I mean, if you give me a lot of zeros, I keep giving you zeros and zeros and zeros. If I only have fixed memory, what will happen to my program eventually? It will crash, one thing is, right? Or maybe it will forget, right? How many zeros it has seen. If I have fixed memory and I keep on giving you zeros, what will happen eventually? Either I can have overflow error, which means that my counters will go crazy, right? I've forgotten how many zeros I've seen, right? So then obviously if I forget how many zeros I see, I can confuse you, right? Yeah? Okay, how do you formalize this, right? So the idea is that, this is not regular and proof, right? We want a proof, right? Yeah? No, NFAs are no more powerful than DFAs, no? So we proved that. If you have an NFA, I can give you a DFA. Yeah. So might as well say, if it is regular, then there must be a DFA for it, right? Sure, but the DFAs are more restrictive, right? So it's better to work with a more restrictive model when we want to prove something is not possible than with a more powerful model. Okay? If I give you more freedom, then the proof becomes harder, that you cannot do it. Okay? If I want you to say that I cannot, if I tie my hand back like I do with DFAs, then you can more easily prove that I cannot do something, no? Okay? If you let me use both hands, maybe I can do more funky things. While if you tie my hand down, I cannot do as much, right? So that's like saying, by using DFAs, we are restricting the model of computation, but we know they're no less powerful than NFAs. No, it's not cheating. Okay, we need to go. Okay. So, how do we formalize this intuition that any DFA which recognizes language must count, but if it counts how many zeros, then its memory cannot be fixed, right? So that's, how do we capture that, right? We capture that by the following proof technique, which is, I'll do it slowly. We say proof by contradiction. Okay, what does it say? We are going to prove that any machine which will accept this, we should get confused. Okay, so how do we formalize that? Okay, so let's play a game. You think that there is a DFA, right? Okay, and I say, okay, you think it's a DFA? Okay, how many states does it have? I don't want information. I just say, how many states do you think it has? You say 1 billion, okay, because you want to be safe, right? You say, look, I think I can create a DFA with 1 billion states, right? Okay, so okay, you have a DFA to accept this language with 1 billion states. I'll give you 1 billion. It's still a DFA, right? Because it's such a big number. Okay, okay. Then I'll say, okay, good. Tell me the following. What does it do when it sees this set of strings? What is this set of strings? Epsilon 0, 0, 0, 0, 0, 0, up to 0 to the billion. So there are, how many strings are there? N plus 1, right? Billion plus 1, right? They're all different strings, right? So what does your DFA do? It's a program, right? Or a fixed machine. On seeing this string, it has to go to some state, no? Yeah? Okay, but I'm giving you billion plus 1 strings and you only have billion states. So what does it mean? What does the pigeonhole principle say? That at some point, the 2 of these strings will go to the same state, no? Okay? Yeah? Okay. So by the pigeonhole principle, I don't know which 2 of these because I don't know your program, right? I have no idea. But I do know that the machine on 2 separate different strings should go to the same state. What does it mean? That means it's now completely confused how many zeros it has seen for these 2 things, no? Yeah? Because if it goes to the same state after seeing 1 0 and after seeing 10 zeros, it cannot distinguish after that whether it has seen 1 0 or 10 zeros. Right? It's confused now, right? What does it mean it's confused? Now if I give you, if it goes to the same state after seeing 0 to the I and 0 to the j, whereas I not equal to j, then if I give it later 1 to the j and 1 to the I, what will it do? Okay, or not 1 to the I give it, so what do we know? We know that there is some I and j, I not equal to j, such that the DFA on 0 to the I and 0 to the j goes to the same state. Okay, now I give it 1 to the I after that, right? So what should it do if I see 0 to the I, 1 to the I? It should accept it, right? Because that's in the language. If it sees 0 to the I and 1 to the j, what should it do? It should not accept it because I is not equal to j, right? But it cannot distinguish them, so it will also accept it. Okay? Right? So once it is confused, we can fool it into accepting or rejecting the right string, right? So, but then you told me that your DFA is the correct DFA, right? But I'm convincing you that it is not a correct DFA. It is getting confused. Okay? Does it make sense? What we did? What did we do? We said, aha, you say there is a DFA, tell me how many states. And I'm telling you, okay, look, I'm asking you what is its behavior on this set of strings. And I've convinced you that because the number of strings is bigger than the number of states, 2 of the strings went to the same state. If that happens, I've convinced you that the machine is not behaving as correctly as you thought it was, right? Okay? This is a formalization of our intuition that if you don't have enough memory, then the machine will get confused because it cannot tell apart 0 to the I or 0 to the j, right? Okay? Questions? This is an important concept. Are you convinced that this language is not regular now? Yeah? You're not convinced? Yeah? Yeah.
So make this argument, like if we were to accept 0 and
No, but this language is given, right? The language is given. Your machine is supposed to accept only strings in the language and reject everything else. Yes, 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 yes.
But we were only considering strings.
No, I didn't consider only strings, that one, right? What I said is that I will feed these strings and look at what the machine does.
Right.
But then, how do I convince you that it is actually misbehaving? I asked you what happens if I give it the string 0 to the I, 1 to the I, and 0 to the j, 1 to the I. I'm asking it what is its behavior on this string and this string, right? I'm giving once now. Now, because it reached the same state after seeing 0 to the I and 0 to the j, it cannot behave differently from this and this. But the language is telling us this should be accepted and this should not be accepted. But the machine is going to behave the same way for these two strings and is going to behave badly. So that's what saying, no, your machine is not correct is what I'm trying to prove, right? So you said there's a machine with n states, and I'm telling you that, look, your machine cannot be right. So that means what is a contradiction? That the existence of a machine is a contradiction. That means that there is no machine there is no DFA for this language. So this is not regular, okay? Is that okay? Yeah? Okay, so that is a proof technique. But we want to generalize this because it is a very specific technique, right? But for this language, I convince you that it's not regular, right? How do we prove it in general? Here is a formal definition which captures this idea. We say two strings x and y are distinguishable by the language L if I can tag a suffix to the x and y such that only exactly one of them is in the language. Okay, what does that mean? So I have x and I have y. What I'm saying is that there must exist a w such that either this guy is in language and this guy is not, or this guy is not in the language and this guy is in the language. Okay, what does it mean? That any machine which does not distinguish these two will get confused, right? Okay, the definition is very important. For a given language L, two strings x and y are called distinguishable if there is a suffix w such that exactly one of xw is in L. Okay. Otherwise, they are indistinguishable. Okay, they are indistinguishable with respect to L if there is no such w. Okay, let's see some examples. Let's look at this language. Remember, this is with respect to a language. Look at the same language we saw earlier. I claim that 0 to the I and 0 to the j are distinguishable for any I not equal to j. So if I have 3 zeros and if I have 5 zeros, then those two strings are distinguishable, right? Why is that? Because you have a 3-0 string and a 5-0 string, I can add 3 ones, right? And one of them is in L, the other one cannot be in L, right? So for any I not equal to j, 0 to the I and 0 to the j are distinguishable with respect to this language. Yeah? Is that okay? Okay, yeah? Definition is okay? Okay, here is another language. Language is W has 0, 0 as a substring. Okay? Now I claim that this string and this string are, the 3 zeros and 4 zeros are not distinguishable. Why is that? Because these both are already in the language, right? If I add a suffix to it, they'll still be in the language. Both of them will always be in the language, whatever suffix I add to both of them, right? Because they already have a 0, 0 as a substring. This, if I added W to it, it will be always in the language. If I added W to it, they'll always be in the language, right? So these are indistinguishable from the language, okay? So why is this notion useful? This notion is useful because if I have a language L and you claim that there is a DFA for that language, if x and y are distinguishable, then the DFA should go to two separate states on those distinguishable strings, right? Okay. If x and y are distinguishable with respect to a language, what does it mean? That means if I add a suffix, one of them is in the language, the other one is not in the language, right? So if you have a machine which cannot tell those two strings apart, then it'll make a mistake, right? Yeah? If I give you two strings where I haven't seen the suffix yet, what should the DFA do? The DFA can only see the current string and it cannot see the future, right? So if after seeing x and y you are in the same state, but there is a string W. If I attack onto one string, it will be in the language, and I attack onto the other string, it is not in the language. I cannot tell them apart, right? So any DFA which accepts this language should make sure that on seeing X, it should go to one state. On seeing Y, it should go to another state, right? If it goes to the same state, it's completely confused. Okay? Okay? So that is the idea. So now what we want to do is like what we did in this particular language, we want to create what is called a fooling set for the language. To prove some language is not regular, we want to claim that, if you have a finite state machine, it will get confused because I'm going to give you a big set of strings which will fool it. Okay? So, what is the definition of a fooling set? A fooling set of strings for a language is a set of strings such that every pair is distinguishable. If any two strings in that set are distinguishable. Okay? Yeah? So that means I give you a big set, say it's called a fooling set, because it says, if you take any two strings, it should be the case that, X and Y are distinguishable with respect to the language. Okay? And example, look at the same language, 0 to the K, 1 to the K. Look at all the strings which are 0 to the I. All strings, it's an infinite fooling set, okay? Every two of them are distinguishable, right? If you have 3 zeros and 5 zeros, they are distinguishable with respect to this language, right? If the number of zeros is not the same, then they are both distinguishable, right? Because why? Because if I tack on 1 to the I, then it will be the language. 1 to the I tacked on to the 0 to the J is not in the language. Yeah? So this is an infinite fooling set for this language. Yeah? Yeah.
So since a language is a set, what if we have the same?
It's a set, so you can't have the same thing. No, right? It's a set. Set means that you have only one copy of the object. No? It's not a multi-set. Right? Yeah. Yeah. So, yeah, is that okay? Yeah. In a set, you can't have two copies of the same. Okay. Okay. So let's see. Here is the point of the definitions is the following, right? If I give you a fooling set of some size, then any DFA which accepts that language must have at least the number of states which is the size of the fooling set. Okay. So let's see the proof of this. Okay. Okay. What does it mean that F is a fooling set? Any pair of strings in that are distinguishable with respect to the language, right? Okay. So suppose there is a DFA for that language that accepts L. Suppose the number of states in the DFA is N, right? If N is less than F, what does it mean? The number of states is less than F. I am claiming that the machine will get confused, right? Why is that? Because take any X and Y in your fooling set. I claim that the machine has to go to a different states on seeing X and on seeing Y. If it went to the same state, what will happen? Because X and Y are distinguishable, there is a string W that I can tack onto X and a W I can tack onto Y, such that only one of them is in the language, the other one is not in the language. But if I reach the same state on seeing X and Y, I won't be able to tell the difference, no? I will get fooled, right? So your machine will get fooled, right? So if I have a fooling set and the number of states is less than the size of the fooling set, by pigeonhole principle, some two strings in my fooling set will go to the same state, right? And then I'm confused, right? Yeah, same argument. What I'm saying is that if you have a fooling set for a language and you have a DFA that accepts that language, the number of states it must have must be at least the size of the fooling set. If it has less states than the fooling set, there will be two strings in your fooling set which the DFA cannot distinguish, and in that case the machine is confused. Okay? So that is the observation, and it is just a formalization of what we did in the simple case. Okay? So now so that's what it's saying, that if your states are too few, and your fooling set is bigger than the number of states, then your machine is not going to behave correctly, right? Okay. Okay. So in particular, if your fooling set is infinite, what does it mean? If your fooling set is infinite, it means that the number of states in your DFA should be bigger than the size of the fooling set, right? That means the number of states in my DFA should be infinite, but that means that language is not regular. Okay? Okay? So how do I prove that a language is not regular? By giving you an infinite fooling set. Not a finite fooling set, but an infinite fooling set. Okay? Yes? Yeah. Okay, let me do some examples. So let's do the example in this methodology, right? It's a little abstract, but we need to understand it. Okay, what is the implicit fooling set we use, right? Okay, say for this, what is a fooling set? I claim f is 0. F is epsilon 0 0 0 0 0 0, which is the same as 0 to the I greater than or equal to 0, is a fooling set for this language. Why? What is the definition of a fooling set? Any two strings in that set should be distinguishable. Why is it the case that any two strings here are distinguishable by that? Because if you have 0 0 and 3 zeros, I can put 2 ones here and that will distinguish this and this, right? Because 0 0 1 1 should be accepted, 0 0 0 1 1 should not be accepted, right? So for any two strings in this fooling set, I'm convincing you that they are actually distinguishable by the language. Yeah? And because it's an infinite fooling set, there is no DFA which can accept it. Yeah? Because if I take any two strings in this, it has to go to two different states. But there are infinite number of strings in this fooling set, which means that the DFA should have infinite memory, right? But that doesn't mean there's no DFA for this. Yeah? Okay, yes or no? But think intuitively, right? What does it mean? It means that you don't have to work with this definition. You have to go back and say, let's go back to first principle. Let's see what a DFA can do on this language, right? Well, if it has a finite number of states, I can keep on giving it zeros till it gets confused. And then there's no way a finite memory machine can remember how many zeros it has seen. I'll keep feeding it zeros till it gets confused, and then I know that it will misbehave. This is the formalization of that argument. Yeah. Yeah. If K over bounded, any finite language is regular, no? Some people may argue, look, the universe is finite, so why do you bother about non-regular languages, right? Well, it's sure, but then, mathematically that's not a good way of modeling computation, because if you restrict the universe to finite numbers, then everything is a DFA, but we know that's not practical, right? So we need to allow infinity to argue about interesting things. Okay? Yeah, question? Fooling set, yes, but that is a not easy proof. Okay? Indeed, if I want to prove that it's a good question. It's a subtle question. It's a subtle question because he's asking, is this a complete proof technique? In the sense that if a language has a fooling set which is infinite size, then it's clearly not regular. But is it the case that this proof technique is complete in the sense that if it is a language not regular, you can always use this technique to show that it is not regular. That means that a language is regular if and only if it does not have a infinite fooling set. And the answer is true, but that's called the Myhill-Nerode theorem, which we don't have time to prove, but it's a very beautiful theorem. I have it in the slides at the end. I won't be able to cover it, but you can look at it. Okay, how do we prove that the number of, look at the language where there are equal number of zeros and ones. All strings which have equal number of zeros and ones. It is a little bit more than this language, right? It is like, this can have this, it can have 0 1 0 1 is allowed in this language, right? Because it has equal number of zeros and ones. So all strings which have equal number of zeros and ones is this language. I want to claim it's not regular. How do you find a fooling set for it? No, remember, this is the language I want us to find a fooling set for the language which is infinite size. What does that mean? A fooling set is a set of strings such that any two of them are distinguishable by this language. Well, distinguishable. Okay. Yeah? Yeah, we can use the same fooling set as above for the same language. I claim this is a fooling set for this language also. Why is that? Suppose I have 2 zeros and 3 zeros, the same proof will work, right? Because these two are distinguishable with respect to this language also, right? Why? Because 0011 is in the language, 00111 is, 00011 is not in the language. If I have unequal zeros, I can tack on ones which are the size of the smaller number of ones, and one of them in the language and one of them won't be in the language. The same fooling set works for this language too, right? Okay, but remember, we have to argue that every pair of strings are distinguishable with respect to this language, and I'm arguing that, right? Because this is a more general language than this in some sense, right? I'll show you another proof technique and why it's more general. We'll see that. Okay, is a method okay? Are you convinced that that's an infinite fooling set for this language also? Yeah. So the same fooling set, but it works for different languages. But you have to prove differently, right? With respect to the distinguishability is with respect to a language, not. Okay. How about this? 0 to the k, 1 to the l, k not equal to l. So that means that I want unequal number of zeros and ones, right? Sorry. So do you intuitively see that I need to count even for this? Yeah? I mean, how can I figure out whether the number of ones is not equal to the number of ones if I don't count, right? Maybe they are equal, no? Okay. Yeah, I mean, it seems intuitive, but what is a fooling set? I claim it's the same fooling set would work, but try to prove it. Take a minute, and I claim the same fooling set which is 0 to the I for I greater than or equal to 0 is a fooling set for this language also. Why is that? The language is changing, but the fooling set is not changing. Okay, but then the proof should depend on the language, right? Because the fooling set is defined with respect to the language. But what is the intuition of the fooling set, right? If I see a number of zeros, if I don't count it, I'm going to be in trouble, right? Okay, but the proof that it is a fooling set for this language, what is it? What do I have to prove? If I give you two strings with different number of zeros, right? 0 to the 5 versus 0 to the 6, then they are distinguishable with respect to this language. Why? Yeah? Yeah, so if I give you 3 zeros and I give you 5 zeros, why are they distinguishable with respect to this language? I can give you 3 ones here, right? And 3 ones here, right? That's a suffix. Now, this should not be in the language, and right? And this should be in the language, right? Right? So this string 111 distinguishes this and this with respect to the language. Yeah? So I have a single suffix which, this is not in the language, this is in the language. Yeah? It's the same thing, right? Same fooling set, but the proof depends on the language, right? Yes? Yeah, no? Yeah? Okay, all right, we have to get used to it. One more example. This is a little more interesting. 0 to the k square. Okay, what is in this language? What do you think is in the language? Okay, epsilon, 0, what is next? 4, okay, 9. Okay, 0 to the 9, right? Okay, and 0 to the 16 and so on. This seems a little funky, no? So now this is not so obvious because it's just all zeros, but we are only interested in lengths which are squares of something, right? So, yeah. Yeah. No, but this language doesn't have 0, 0, no? 0, I mean, these are integers, right? 0, 0 is not in the language. I should not accept 0, 0. I should not accept 0, 0, 0. But I should accept 4 zeros. No, it's not a subset because here there are ones. Yeah, sure, yeah. It's a subset of this, but this is a very different language from this, right? Because it has ones allowed. Here there are no ones. This alphabet is only 0. Okay, yeah? Yes, I'm trying to make a fooling set for this. Yeah, but I need an infinite fooling set. Yeah, but what does it mean keep going? You're telling me the description of the set, no? Right, you're telling me what are all the strings in that set. And it has to be infinite, so you can't write them down, right? So you have to give a formal description of why is it infinite, right? So my claim is, I mean, this is a little tricky one, yeah? Good. This set itself is a fooling set, okay? This is a tricky one because it needs some basic algebraic manipulation. It's the same thing. L itself is a fooling set for itself. This is a little subtle, but I don't care, right? It's an infinite set. So what does it mean? It says that, what I need to prove to you that it's a fooling set. So if I give you two strings in the language, in the fooling set, remember, what does a string in this fooling set look like? It is 0 to the I square for some I, right? And 0 to the j square for some j. They are different, so I is not equal to j. I want to claim that these two can be distinguished by this language. How can they be distinguished? That means what do I need to prove? I need to prove that there exists W such that 0 to the I square W and 0 to the j square W, only one of them is in the language, the other one is not in the language. So what length of zeros, what is that W going to be? How can I make sure that only one of them is in the language, exactly one of them in the language? We know that, say, without loss of generality, I is less than j, okay? Yeah? Good, right? So what can I do? I can choose W to be 2i plus 1, right? 0 to the 2i plus 1. Now what is this string become? It will become 0 to the I plus 1 square. What does this string become? Well, it will become 0 to the j square plus 2i plus 1, right? I want to claim that because I is less than j, this cannot be a square. It cannot. See, what is the next square after j? J plus 1 square, right? But j plus 1 square is bigger than this, right? So I cannot get to a square by adding a small number, right? So this is in the language, this is not in the language. Yeah? Okay, it's a little tricky, no? So I and j are different. Without loss of generality, I is less than j, right? So if I add 0 to the 2i plus 1 to this string, I will get 0 to the I plus 1 square, which should be in the language. But if I add it to j square, I won't be a square, so it is not in the language. I'm making sure that these two are distinguished. Yeah? But why is it not a fooling set? You can try that, but can you prove that for any 0 to the I and any 0 to the j, that there exists a suffix such that they are exactly one of them is in the language and the other is not in the language? It will be a lot harder. Maybe it's true, but you have to prove some property of that, right? Yeah, the fooling set doesn't have to be unique, right? It just has to be infinite to prove it's not regular. Yeah. No, for every language there is a fooling set. See, each of these languages I'm creating a different fooling set. Right? We create a fooling set for a particular language, these are just examples of different languages. where I'm able to create an infinite fooling set. So if I create an infinite fooling set, then you know that it's not regular. Okay? Let me give you another important example. This is a very fundamental example. We saw this language before. What is this language? It is parameterized by a number k. It is a set of all strings such there is a 1 k positions from the end. Okay, pick k to be 4. What are the strings in this language? For simplicity, k equals to say 4. What are strings in this language? Let's recap the understanding of this. It means that I should have 1 followed by some 3 things, right? 3 things, and I can have any prefix, right? Those are all the strings in this language. Yeah? Is this language clear? Yeah? I should see 1 k position from the end of the string, right? So remember, what did we do? We created an NFA for this with k plus 1 states, right? What does the NFA do? It sits around waiting, and then it guesses the 1, and then it has to see k minus 1 more symbols, right? So it is a very compact NFA for this, right? K plus 1 states. But if you want to create a DFA for it, we couldn't do anything which did not remember all possible suffixes of length up to k. It has to remember the last k things it has seen, right? But there are how many such suffixes are there? It has to remember 2 to the k things, right? So I want to prove to you now that any DFA for this language, it's regular, right? For any fixed k, it's regular. But I'm going to prove to you something very nice, that every DFA that accepts L to LK has at least 2 to the k states. How can I prove that to you? By giving you a fooling set of size 2 to the k. If I give you a fooling set of size 2 to the k, it means that no DFA with less than 2 to the k states can accept this language. Here, it is a regular language, right? But I'm proving you that a DFA which accepts this language has to be big. Okay? That also shows that why there could be compact NFA while the DFA for it can be huge, right? So how can I give you the fooling set for this? Okay, I claim this is a fooling set. All strings of length k, they form a fooling set for this language. All strings of, so pick k equal to, for concreteness, let's pick k equal to 5. Okay, all strings of length 5, that's the fooling set for this language. What does that mean? So here is what I'm claiming. How do I prove that it's a fooling set? So if I give you 2 strings, 0, 1, 0, 1, 0, and 0, 1, 1, 0, 1. I claim these 2 are distinguishable by this language where, you remember here k equal to 5 for simplicity, right? Why are they 2 distinguishable? What does it mean? I should put some W here such that only one of them is in the language, the other one should not be in the language. Can I do that? What W should I put so that one of them is in the language and the other is not in the language? Yeah? Yes? Yeah, so let's look, why are they different, right? If they're different, that means that there is one place where this guy is 0 and the other guy is 1, right? Okay, so I will add a suffix so that that guy becomes the kth bit from 1, right? So let's add, what should we add? Any string of length 2 will suffice. Right? No, length 2 or, yeah, length 2. Let's add a string of length 2. So if I add a string of length 2, what will happen to the string? I'll get 0, 1, 1, 0. I added 2 symbols, right? The same 2 symbols. Let's call them A, B, and oops, 0, 1, 0, 1, A, B, right? Now I claim, well, this string is not in the language while this string is in the language, right? Why? Because k equal to 5, this guy has a 0 in the 5th position from the end, this guy has a 1 in the 5th position from the end. Yeah? So this guy is not in the language, this guy is in the language. So if I give you 2 strings which are differ, that means that there is a first place where they have, one guy has a 0, the other guy has a 1, right? Then I can pad some extra symbols so that when the string finishes, one guy will have a 0 in the kth position from the end, one guy will have 1 kth position from the end. So any two strings of length k are distinguishable by this language, which means the size of this fooling set is how big? 2 to the k. So no DFA with less than 2 to the k states can accept it, because if it takes any two of those strings to the same state, it's going to get confused, right? It cannot differentiate them. That's the meaning of the fooling set. So this is an example of a language with a finite fooling set, because it is regular, right? We know it's regular, it cannot have an infinite fooling set. But it's a finite fooling set, but we are able to use the size of the finite fooling set to argue that any DFA which accepts this language should be big. Okay? We're proving a lower bound on the size of the finite fooling set. Okay, we'll stop there. Okay?
This WPM
It can be epsilon too. For example, if it is 1 0 0 0 0 and 0 1 0 1 0, epsilon is a distinguishing sign.
So W could be
Epsilon. Yeah, W could be epsilon. Yeah. Yes. Yeah. Yeah.
Can you explain the definition of the LK? It's one
K position from the end. That means that if you look at the string, if it has length k less than k, it is not accepted because there is no 1 k position from the left. If it is longer than k, it should have 1 from the other side.
So let's say you have a string bigger than k size, but after k elements, k.
No, so k is fixed here. So think of, for every k there is a new different language. So think of k as 5 here. So what is L5? L5 is a set of all strings which have a 1 5 positions from the end. Okay. So if there's a 0 in that position, it's not in the language. If it's 1, it is in the language. So here is a so let me say so k equal to 5, right? 0 0 1 0 0 0 0 1 0 0. Is it in the language or no?
It's not.
Yeah. So that's it, right? If I give you to make it be in the language, it should have a 1 here. Okay. If it has 0, it's not in the language. Yeah.
So I have a question. So you mentioned that any DFA can be encoded into a string, right?
Yeah.
So can you always simulate a DFA with another DFA? Because I heard that Turing machine can do that.
Sure, but we have already seen that we can even simulate an NFA with a DFA. So it's not going to
input a string encoding for a DFA and
no.
string as an input.
No, it cannot do it, right? Because it can't even. Okay. So, for example, it can't even. Let me turn this on.